Okay, so we've looked at Newton's three laws of motion, and we've looked at how to represent forces acting on objects through free body diagrams. Now we're going to use these laws and skills to solve various force and motion problems. Basically, we're going to be looking at problems without friction first, and then problems with friction. And these pictures are representations of various standard problems that we're going to be looking at. We're going to begin with equilibrium problems. Equilibrium means the net force is zero. There's basically two types of equilibrium problems. First, there's static equilibrium and dynamic equilibrium. With static equilibrium, the object is at rest. In dynamic equilibrium, the object moves with constant velocity, so zero acceleration. The kind of the hallmark of equilibrium problems is that the net force acting on an object in equilibrium must be zero. This traffic light sitting here, if that's our object, it is in static equilibrium. So because forces are vectors, we can look at them in terms of their x and y components. So when we look at all of the forces acting on a single object, we split up the components that all act in the x direction, and we split up all the components that act in the y direction. And when we have equilibrium, the net force in the x direction and the net force in the y direction add up to zero. So let's look at an example. We have a wrecking ball, weighs 2,500 newtons, hangs from a cable. Prior to swinging, it's pulled back to a 20-degree angle by a second horizontal cable. What is the tension in that horizontal cable? So what we have, here's our wrecking ball, and we've got our horizontal cable here. We've got this cable that's held back at a 20-degree angle. We know that the force from gravity on the wrecking ball is 2,500 newtons. We are looking for the tension in that horizontal cable, but neither do we know the tension in that angled cable. So we're going to begin this kind of problem with making a free body diagram. We begin with our axes and represent our object, the wrecking ball, as a point mass. And then we can begin to add in the forces that act on that wrecking ball. So we have a weight force that points straight down, so force from gravity. We have a tension force, this is T2, that acts at an angle, and that angle reported is this angle right here, of 20 degrees. And we have the horizontal tension here, T1. And it's T1 that we're going to be looking for. Now, because this is an equilibrium problem, that tells us that the net force must be 0 newtons. Okay? And because it's an equilibrium problem, the net force is 0. That means the net force in the x direction must also equal 0, and the net force in the y direction must also equal 0. So what we have to do is begin to look at all of the forces that we have in the x and y direction. So let's look first at the x direction. Here we've got tension 1 in the x direction. We've got tension 2 has components in the x direction and y direction. So here would be T2x and here would be T2y. And we're going to put those into our expressions down here for our forces in the x and y direction. So in that x direction I have just T2x and T1. So, and T2x points in that positive direction. So I can go T2x, T1 points in the negative direction, so I can subtract minus T1 equals 0. In my y direction, my T2y points in the positive direction, and force from gravity points in the negative direction. And both of those are going to equal 0. So now we have to look at how do we solve for T2x and T2y. So if we look closer at T2 itself, we can see here this angle. This is kind of what we've got here. This is our reported 20-degree angle here. Right here, this is our T2y, and here's our T2x. So T2x is opposite our reported angle. So we can come up with an expression for T2x like this. So we've got an expression for T2x here. It's T2 sine theta, because that T2 is opposite that reported angle. We can substitute that into our expression over here for T2x, giving us this right here, T2 sine theta minus T1 equals 0. The problem is we don't know what T2 is, so we're going to have to look into our y direction to figure that out. When we do so, we get T2 cosine theta, because T2y is adjacent to the reported angle. And we've got our force of gravity here. Now we've got something that we can start plugging in, because we know what our weight force is. So we get T2 cosine 20 degrees minus the 2500 equals 0. It's an equilibrium problem. It's going to equal 0. So we end up with T2 equals 2660.4 newtons, which we can then take and substitute in right here in our expression for the in the x direction, so we can find T1. It would look something like this. And solving that tells us that T1 then is 910 newtons. So that's an equilibrium problem of static equilibrium. And then just remember, for a dynamic equilibrium problem, the same rules apply, is that our net force adds up to 0, even when an object is moving with dynamic equilibrium. So now, let's look at dynamics and Newton's laws. So this will be cases when the net force is not 0. In these cases, forces acting on an object determine its acceleration. That's Newton's second law, F equals ma. Then the object's motion can be found by using the acceleration we find here in equations of kinematics. So the main thing to understand with these types of problems is that our net force now is going to result in an acceleration. And again, because force is a vector, we can look at it in the x direction or the y direction. So if we have an acceleration in the x direction, that means that there's a net force in the x direction. If we have an acceleration in the y direction, we have a net force in the y direction. It's not necessarily always the case that there is an acceleration in both the x and y direction. Okay? We could have 0 acceleration in the y direction and a positive acceleration in the x direction, for example. So let's look at a couple of examples here. A golfer puts a 46-gram ball with a speed of 3 meters per second. So friction exerts a 0.02 Newton retarding force on the ball, slowing it down. Will her putt reach the hole 10 meters away? Okay, so here's what we know about this. We know the mass of the ball. We know the frictional force acting opposite the direction of motion. We know it begins at 0 meters. We know that it ends at 10 meters. We know that it is moving at 3 meters per second, and its final velocity will be 0. So this thing is slowing as it moves down here. So we have an acceleration. That tells us we do have an acceleration in the negative direction this way, and we're looking for eventually this. So we're going to begin, as always, with force problems by drawing a free body diagram. And this is what it would look like. So we've got the weight force here, we've got the normal force here, and the frictional force here. Notice there's no other forces in the positive x direction. That indicates to us then that we have an acceleration in the negative x direction, and therefore there's a net force there. So if we look at the force in the x direction, then this is just the x direction, we have just that frictional force, which is going to equal the mass of the ball times the acceleration in that x direction. So our frictional force, we're told, is a 0.020 Newton force. It's in the negative direction, so we make sure we show it's negative. And then our mass of the ball is this 0.046 kilograms, and we can find our acceleration. Notice that I've converted it's given to us in grams, converted to kilograms. We always have to make sure that we do that for these problems to work. Okay, so we see then that we have an acceleration of negative 0.435 meters per second squared, and now we can take that acceleration and put it into a kinematics equation to then solve for our displacement. And we end up with this displacement of 10.34 meters, showing us that yes, she will make that putt. Okay. So in this example, we have a car with a mass of 1,500 kilograms being towed by a rope held at a 20-degree angle. We got a frictional force of 320 Newton opposing the car's motion. We want to know the tension if it goes from rest in 12 meters from rest to 12 meters per second in 10 seconds. So in this problem right here, I've included all the things that we know, what we're looking for in the free body diagram. And just in the interest of time, I'm going to go through this very quickly and just sort of put the worked out problem on the screen. Make sure you pause and take a look at it. So now what we're going to do is look at some specific types of forces and apply Newton's laws to them. We're going to start with the weight force, then we're going to move on to what's called the normal force. So let's think about mass for a minute. Mass is a physical property of an object. All objects have a certain amount of mass. Weight is the force with which a gravitational field pulls on an object with mass. So weight is a force from the Earth's gravitational field. So suppose we have a big truck and we have a small car, and we want to accelerate those two objects at the same rate. Which of these objects would require a greater force to accomplish that? Obviously, the truck. If we want to accelerate both of these at the same rate, we're going to have to push harder on the truck in order to accelerate it at the rate we want to. So the same is true then for Earth's gravitational field, right? So in Earth's gravitational field, everything accelerates at right about 9.8 meters per second squared. We can round it up to 10 meters per second squared for our example. If we got an elephant then and a mouse, the elephant is going to have to be pulled on harder by the Earth than the mouse will to get it to that 10 meters per second squared. Okay? Now, since Newton's second law tells us F equals ma, right, we can take our acceleration and make it g in this case, right? So weight is the force of Earth's gravitational field pulling all objects toward the center of the Earth. And it's a force. So the weight of an object is the force of gravity on that object. You might not have ever thought about it, but gravity is not a force that you can feel or sense directly. Your sensation of weight, how heavy you feel, is due to the contact forces pressing against you. When you stand up, you feel the force of the floor on your feet, right? You're not actually feeling the earth pulling you down. What you're feeling is the floor pushing back on you, and you get that sensation of weight. For example, this man here is standing here. He feels the normal force of the floor pressing against his feet. So when he stands at rest, the magnitudes then of the normal force and the weight are equal. Now it's really important to understand too that this normal force and the weight are not an action-reaction pair. Action-reaction pairs act on different objects. Okay, so the weight here, his weight is because of the force of Earth's gravitational field pulling him down. The normal force is because of the force of the floor back on him. So the action-reaction pair to weight would be his gravitational field pulling up on the Earth, while the action-reaction pair to this normal force would be a normal force from his feet onto the floor. Okay? So now let's imagine we take this guy and we put him we put him on a spring scale and put him in an elevator, and we begin to accelerate that elevator upward. For the net force then to point upward, the magnitude of the spring force has to be greater than the magnitude of that weight force. This has pretty big implications. If we look at this free body diagram, we see that the y component of Newton's second law becomes this right here. Our net force then is equal to the mass times the acceleration in the y direction, and where m is the person's mass. The scale reading is the value of that spring force, the magnitude of the force that the scale exerts on the person. So solving for this spring force will give us his weight plus MAY. If that elevator is at rest then, or moving with a constant velocity, acceleration is 0, and they're in equilibrium. If we have an acceleration greater than 0 then, the scale's reading is not the man's true weight. We define an object's apparent weight as the magnitude of the contact force that supports that object. So when there's no acceleration, the person will stand, they feel normal, they feel the weight of the elevator pushing back on them as they normally would. When we have an upward acceleration though, the bottom of the elevator pushes up harder on them. The normal force on the person increases and he feels heavier. Okay? When he has a downward acceleration, the floor pushes up on him less, and therefore he feels lighter. Notice though, in each of these cases, right, his actual weight remains the same. What changes is what's called his apparent weight. It gets greater when we're accelerating upward, and that apparent weight lessens when he is accelerating downward. If the elevator were to break, both he and the elevator would be in a free fall situation, accelerating at the rate of g. Alright, so now let's look at normal forces. So imagine something, an object, something like a television, sitting here on a table. We know that the gravitational force is acting on a television, but how can we use Newton's laws then to explain why that television does not continue to just fall toward the center of the Earth? So if we analyze the forces acting on that television, right, we can see that it does have the Earth's gravitational field pulls down on it, but because of the surface of the table, there is also a force pushing up on it. We call that force the normal force. We use the word normal because it is perpendicular to the surface that we are looking at. Right? So the normal force is one that acts perpendicular to whatever surface we've got. So if we have an object sitting on a tilted surface on a ramp, all right, the normal force acts perpendicular to that surface. The weight force will still act straight down toward the center of the Earth. That's always the direction of the weight force. The normal force is always perpendicular to the surface that the object is on. So now then, let's look at when we have, say, two objects on a surface here. Okay, here we've got two boxes, box 1, box 2, sitting on this surface. So we're going to look at the forces on each box. Box 1 has its weight force from Earth's gravitational field. It has a normal force acting on it from the surface. And then it also has, because of this surface here, it has a normal force from box 2 upon it. Now this normal force then is equal to not just the weight of the box of box 1, but equal to the weight of box 1 and 2 together. So box 2 then has a normal force acting on it in the upward direction from box 1, and it's got a weight force from Earth's gravitational field acting on it, pulling it down. Okay, so now let's look when we have a normal force acting on an incline. So like I've said, the normal force always points perpendicular to the surface. If we rotate then our x-axis so that we're on a surface, our weight force will always point straight down, giving us then an angle sitting here. So by rotating that x and y axis to match the surface, we can see that the angle between the weight and the negative y axis is the same as the angle of the slope. A lot of time what we'll see then is our angle of our slope reported as this angle right here. This angle here is the same as this angle here, same as this angle here. You can go ahead and do your own analysis of that to see that. So the weight can be decomposed then into its x and y components. We can get our weight y sitting here, we get our weight x sitting here. Then our weight x then is w sine theta, and our weight y is w cosine theta. Okay, a couple mistakes to really avoid is showing that normal force not perpendicular to the surface of it when it's tilted. We always show it perpendicular to the surface, and then also the weight does not point perpendicular to the surface along the y-axis, negative y-axis. It points straight down. So one final example, if we have a 1.2 kilogram book lying on a table, the book is pressed down from above with a force of 15 newtons. We want to figure out the normal force acting on the book from the table. So here's our book on our table being pushed down by, that's a hand right there, being pushed down from above. We then have a weight force pointed downward. We also have then the force of that push, pointed downward. And just incidentally, on these free body diagrams, right, if you've got two forces acting in the downward direction or in the same direction, we can just kind of bring it out and bring it down. Okay, that's pointing downward. It doesn't mean that it pushes out and then down. It just means that it's pushing down. It's just a way to draw it. And then so there we also have a normal force from the table pushing up. So our net force here in our y direction then, we've got our normal force minus this force of the push minus this weight force equals 0. And we're subtracting them, of course, because they're pointing in the negative direction. So in looking at this, right, this we have the force of the push that's given to us up here in the problem. We also now have an expression for our weight force here. Okay, our expression for weight force is mg. So here now we've kind of fully pulled out everything in our equation. So our normal force then minus that push minus the weight 1.2 times 9.8 equals 0. And so when we go to solve this, we end up with a normal force of 26.76 newtons. Okay, so that's that for now. Take a look at example 9 in your notes packet, the acceleration of a downhill skier for a case when our surface is tilted. See you in class.